I would like to present a lecture that I've been giving sort of over the spring of 2017 that kind of captures a lot of the thoughts that myself and my group have been working on around data-driven discovery, mostly related to dynamical systems or partial differential equations with applications towards engineering and physical and biological sciences. So this is work done both by myself and colleagues, collaborators, postdocs, and students here at the University of Washington. And I'd like to just walk through the main ideas and methods and also point you to my website afterwards where a lot of the code used to produce the things here are going to be available. So let me start off with three primary concepts I'm going to run throughout this talk. One is AX equal to B. This is going to be the primary mathematical framework we're going to work with. So it's actually not that sophisticated, but there's a lot more to AX equal to B than we normally think about. And I want to talk about some of that so that we can get an idea of how we want to think about AX equal to B, especially in a data-driven world. The other thing we want to talk about is model selection. There's a lot of ideas for model selection extending all the way back to the 1950s that we can start to integrate now with some of the concepts we want to bring together. And finally, the idea of dimensionality reduction. Dimensionality reduction is an important concept in which instead of working with high-dimensional subspaces, you find a way to embed your data into low-dimensional subspaces. So let's start off with this. Most of us feel fairly comfortable with AX equal to B, and I suppose what I'd like to say is that there's a lot more to AX equal to B than meets the eye. In fact, we want to do a lot more than just do a backslash in MATLAB, for instance. So, and the reason there's a lot more to AX equal to B is that in a data-driven world now, we often think about data matrices being either highly under or over-determined. So often I can collect data from a few variables, let's say for a very long time. So in that case, I have something like this over-determined system where the rows would be time snapshots of states of a system, and I have this large collection of variables, or potentially I have a bunch of gene expression data, 20,000 genes, but I have very few samples. So these under and over-determined cases means that we're not working with square matrices anymore, where a square matrix you can get a unique solution, provided the matrix itself is not singular. Here we've got to make some choices. When you're over-determined, right, that means you have a lot of constraints with few variables. It means that you can't actually satisfy the equation, so you have some choices to make about what kind of solution do you want to get back. And oftentimes it's associated with minimizing some kind of error. Same thing with underdetermined systems, where you have a lot of variables, very few constraints. It means you have an infinite number of solutions you could put forward. Which one should you actually use? So this is kind of the framing of what we want to begin thinking about AX equal to B. And here's just a little snippet of MATLAB code. I'm going to just show you a system where I've got, I make a matrix here, A, just out of random numbers, which actually has 500 rows, and 100 rows and 500 columns, right? So I have 100 constraints, 500 unknowns. So it's highly underdetermined. That means an infinite number of solutions available to me. Which one should I pick? Now, normally in MATLAB, you might use something like this. Just use your backslash command. Or you could use something like this, which is a pseudo-inverse. And actually, there's a lot of other AX equal B solvers available in MATLAB. Lasso, Ridge, Robust Fit, a lot of AX equal to B solvers. All of them giving you something slightly different. What I show you here in this picture is when I solve AX equal to B, I'm going to decide on a metric for you. And one of the things I can do, for instance, is I could say, how about if I give you back a solution that has the smallest L1 norm or the smallest L2 norm. And what these are histograms of the distribution of the values of the X vector, which is 500 components. And what you see here is some different solution techniques which give you very different things. If you do L1 optimization, which is approximative sparsity, and this is something we want to think a lot about in this lecture, is you can see it gives you about 400 zeros and then 100 unknowns which are spread out here. You can barely see them, but you can find that I get 100 non-zero components and 400 zero components. So this is like a sparse representation of the solution, all by just simply give me a solution that minimizes the L1 norm. The backslash in MATLAB Maybe you did not know what it did, but what it actually does is a QR pivot routine, and it actually gives you also a sparse solution in the case that here, like this one here, where you're highly underdetermined. And here, this is actually a different solution than the L1 optimization, but it is sparse. The pseudo-inverse is a least square algorithm, fitting algorithm. What it does is says, look, I want to minimize the L2 norm. And by the way, just to show that specific more clearly, if I actually do L2 optimization, pseudo-inverse and L2 actually match. So what it tries to do, since it wants to minimize the L2 norm, it makes everybody very small, because when you square a small number, it's even smaller, and when you add them all up, it minimizes this L2 norm. So which one should I use? In these cases here, all 500 values are non-zero, whereas up here, I get a selection of components that are non-zero. As I said, there's probably 6, 7, 8 different AX equal to B solvers in MATLAB, all which will give you very different solutions for under or overdetermined systems. And so that's something we want to start thinking about in the framing of the problem we have for model discovery. So let's talk about model discovery, because that's ultimately what we're going to do. We're going to take time snapshots of data, and from those time snapshots, we're going to try to reconstruct the dynamical system or the partial differential equation that gave rise to that data. And so we're going to need some framing for this, and a very nice framing has been thought about for a long time, this idea of model selection. It goes all the way back to the 1950s in this idea of KL divergence or Kullback-Leibler divergence. And the idea was, I make a model up from whatever intuition I may have, or conservation laws, or some kind of physical constraints that might be available in the model. So I write down a model. Now this model may or may not, we don't know how good this model is, but what I can do is run my model for lots of trials with different, let's say, noise realizations, and I can look at my measurements of the data itself, which would have some statistical distribution, and I can compare basically the statistical distribution between my model and the actual data, and this is the KL divergence metric, which tells me how far apart those are. Now this is formalized in the 70s with Akaike information criteria, so AIC. And what this did is said, instead of you giving me one model, how about you give me a suite of models, anywhere between 6, 10, 12, 4, a handful of models that you may come up with where you want to say which one of these models is most representative of the data. And so what you would look at is the relative distance between the model that you choose, one of these models, to the actual data itself. Whoever has the lowest score is in fact the correct model. So we have to think about the correct model in quotes here, because what it's just giving you is the best model out of the ones you've given it to evaluate that is most aligned with the data. In 1978, there was an important innovation around AIC, which was by this Greg Schwartz, a Bayes information criteria, and BIC in 78. The important piece of BIC was that if you have a selection of models, if the right model's actually in there, okay, and if you have enough data, then in fact the BIC criteria is guaranteed to converge to the right model. Now in AIC, that is not necessarily the case. It's not guaranteed to converge. So the BIC criteria actually was a very important innovation, because it gave you a mathematical guarantee of when this information criteria can actually converge to the right model. So normally this is done with a limited set of models. So you give me anywhere between 4, 5, 6, 10, 12. You don't give me thousands of models. You give me a handful to evaluate and to look at and compare to the data. Now the way that the BIC or AIC works is, I want to illustrate it on this chart here. So on the y-axis is the error, and on the x-axis here is what we're going to call the parsimony of the model, or the complexity of the model. So really it's the number of terms in the model versus the error. Now if you give me 1,000 data points, I can give you a model with 1,000 degrees of freedom, and I can give you 0 error. But the problem with that is I've massively overfit that data. So the idea of parsimony, or what's called a Pareto front analysis, is to look at the error versus this complexity. And what AIC does, it penalizes the information by the number of terms. So obviously, if you have more terms, you will be able to fit data better. Just because you have more degrees of freedom, it does not mean it's the correct terms. You've just added more parameters to bring your error down. And what AIC does is says, I'm going to penalize the number of terms, and I'm going to also add in here the likelihood function, the log likelihood function, to evaluate the difference between a model and the data. And so the idea behind this is that over here on the left, if I have no terms in my model, in other words, I assume that the model is dx dt equals 0, in other words, I have a constant, then that is the maximum error. I haven't done any fitting at all. I just picked one parameter to fit all the data. That's sort of your maximum data. But as you pick a lot of terms, your error should go down. In fact, as the number of terms equals the number of data points, your error goes to 0 because you're actually overfitting. Now, somewhere right here where it takes a bend, and right here is the region of interest to us. This is called the Pareto front. Okay? Notice that because of AIC, the way it's defined, there's a slope here of 2, which is this term here, this 2k. This 2k tells you that I'm going to penalize by 2 times the number of terms, which is going to make this go up here, so this is going to be, the error is going to go up here, so it's going to be disadvantageous. Whereas here, this is where I'm balancing model complexity and the error in some kind of principled way. This is what AIC and BIC can do for you, is to look at models in this region and evaluate them to see which one is the best. Okay? So this is these are sort of the key ideas behind model selection. The other thing we want to think about is this idea of dimensionality reduction. I'm working in some high dimensional space. It could be I can find some low dimensional space to embed my data in. And so the idea is to transform from my original space to some low rank space times weightings into that low rank space. So if I have a time dynamic system, potentially I can find a rank R set of modes which optimally embed the data. Okay? That's a very important concept that we're going to use throughout, and it's used throughout machine learning, throughout reduced order modeling, and a lot of infrastructure in terms of thinking about data science. So let's go to the workhorse of this dimensionality reduction, which is the singular value decomposition. So the idea is you take a data matrix, and what you want to do is you want to do a singular value decomposition, which is guaranteed to exist for any matrix, and it breaks it up into 3 matrices. 2 unitary matrices, U and V, as well as the diagonal matrix C. And what the diagonal matrix sigma there does, it tells you the ordering and the strength of each of the modes in the system, or how much correlated activity with each mode. The U columns of U, in fact, give you your low dimensional subspace, and the columns of V tell you how each mode here is evolving in time. So for every single low rank subspace mode, there is a time evolution associated with it. That's if we assume that this matrix here is space versus time. Okay? And what we want to do is look at the diagonal structure of this to see what are the dominant modes and pull the R dominant modes out of the data, and that will be our low dimensional subspace where we're going to embed all of our dynamics in. Now, the SVD is not the only way to think about data reduction or dimensionality reduction. The other things like tensor decompositions, where you take data cubes, or more generally n-way arrays, and you can decompose them into constituent parts in each direction. So it turns out to be sort of an outer product of low-rank structures, all of which span a different direction in the data in the n-way array. Okay? So tensor is also a powerful concept, and you can do things like SVDs in tensor space. One example of this, and I'll tell you about the work of Bethany Lush, who is a postdoc here and was a PhD student and is now a postdoc. We looked at this and looking at the kind of analysis that we did here was looking at sort of the dynamics of Houston, the crime data in Houston over time and space. And interestingly, one of the reasons why you want to use a tensor decomposition is because oftentimes if you have higher dimensional data, the standard trick in data science is to flatten your data into a big vector. However, the different directions of the data here, it does not make sense to flatten your data, because in one direction the data is categorical. It's the type of crime that might be happening, whether it's aggravated assault, theft, robbery, and so forth. Those are the kind of crimes that we have. And then the crime type, so we have the crime type, the time of day, and the amount of crime. So you don't want to just flatten these into a big vector, because it doesn't make sense to mix time crime with how much is happening of that crime. So what we can do is, by keeping the data separate, you actually can get these very highly interpretable modes around what kind of crime type there is, how this crime type happens during the day, and which region it's associated with. So it's a very nice diagnostic tool for higher dimensional data sets. And you can use this, and again, as a low dimensional embedding tool if you want to extract these out. One other very important concept is associated with the fact that if you have extremely large data, and you know this data is going to be embedded in some low-rank subspace, then you shouldn't be doing the SVD on this very high-dimensional system. Instead, you could do things like randomized linear algebra techniques, where you can massively subsample your data through a random sampling matrix, do a QR decomposition, and then produce, in fact, an approximation to the SVD with very limited sampling of the data matrix. I actually think this is one of the most important techniques that people aren't using. This is sort of fundamental, and in any case when you have very large data sets, randomized linear algebra methods should be used if at all possible. It's just a very powerful technique. It's computationally efficient. It's the right kind of strategy to think about handling very large data structures. And this was work we did with Ben Erickson. We've actually put out a lot of open source code on randomized linear algebra packages, both in terms of tensors, dynamic mode decomposition, and SVD. So you can download these packages. They're very easy to use, and they're computationally extremely efficient. And Ben Erickson here at the University of Washington doing a postdoc as well, and we've been doing this using this kind of format for taking care of high-quality video, HD video. So when you take HD video streams, we're starting to get into the age of 4K and 8K video, where each single snapshot of a video has on the orders of tens of millions of pixels. So now if you take lots of snapshots in times, your data matrix is getting enormously large. However, even though there's an increase in the number of pixels sampled, the intrinsic rank of the objects or the features of interest in the video have always remained the same. And so why would you scale your computation when, in fact, you can look at some target rank features, and this is a pathway forward to doing this very efficiently and potentially real-time processing of HD quality video. Okay, so those are the underpinnings. AX equals to B, some ideas of model selection, as well as dimensionality reduction. So what we want to start looking at is now some of these physical systems we want to explore, which really exhibit low-dimensional structures in their dynamics. And I'm going to give you a set of picture here, which kind of shows what I'm talking about. So in each picture is a very different physical system. From down here at the bottom, which is an atomic condensate, you can see that all these hundreds of thousands of atoms are actually localizing in a very specific way, producing a low-dimensional structure, coherent structure. This is an optics field. Here you have these large coherent structures in a wake behind a jet. Obviously this is a hurricane structure. This is granular flow that produces these macroscopic patterns. And the most interesting one to me actually is this one here, which is recordings from the antenna lobe of a locust. And these are neurons that you can record from. And this is work from Gilles Laurent's group in 2008. And it very much attracted me to neuroscience, because I think this has this very interesting features in the data. If you look at this recording, spike train recordings, when they apply an odor, it looks like a kind of a mess. It just looks like firing rate activity that's there, spiking neurons. The question is, how do you interpret this? Well, one of the things they did is they took this data, they looked at the firing rate, which is some kind of integral over the spiking, and then they did a singular value decomposition. What you find in this case is when you're applying the odor, everything collapses down to some very simple low-dimensional dynamics, which is your activity sits here, and as you apply an odor, you take these paths up to this fixed point, and you turn the odor off, you come back down. Turn the odor on, turn the odor off. This is a three-dimensional subspace spanned by principal component direction 1, 2, and 3. And what it shows you is all this collection of neurons, and there are a lot of neurons interacting here. We don't even know their connectivity structure and the wiring diagram of this, but what it's showing you is that this antenna lobe is processing data in some coordinate system where it just looks like it's three-dimensional. And there it is right here. This is an important concept because it tells you that maybe you should be writing your model in these coordinates, not these. And that's really the underlying concept of what we want to approach here, which is, can I find the good coordinates, good observables, that will allow me to best represent my dynamical system? So what makes this difficult? Nonlinearity. I think this is the most interesting thing. This is why I got very interested in dynamical systems, is because nonlinearity plays this really interesting role of producing all kinds of interesting phenomena that we work very hard to try to explain. And so nonlinearity is at the heart of producing a lot of the physics or observations we want to see that are very robust and interesting and hard to quantify. But part of how we're going to go after this is we are going to look at dimensionality reduction techniques like the singular value decomposition, dynamic mode decomposition, tensors. There's a lot of other matrix factorizations. This is going to allow us to sort of think about subspaces where dynamics happen. Then we also want to think about observables. What I mean by that is, what kind of things should I be observing? Just because you recorded from some variable doesn't mean it is the right variable to use. So we can start thinking about ideas from Koopman theory or Tocken's delay embeddings. We think about manifold learning. There's a lot of concepts down here I will get to later in the second half of the talk that we can really kind of go after, which is I maybe want to figure out, is there a better set of variables I can place myself in that's going to better extract out the kind of dynamics I want to look at. So here are the goals, though. With those being the difficulties of the tools, the goal are kind of along here, which are, the first thing is just to think about using these tools for diagnostics. You know, how can I pull out features? How can I get interpretable features out of the dynamics to help me learn something about the system? I want to do some future state prediction. That would be ideal if I can take my data and tell you where the system is going. I would love to discover the actual nonlinear dynamics of that system and think about that might set me up to be able to think about controlling that system. There are some really important challenges that are at the forefront of applied math and scientific computing. One is this idea of multi-scale physics. We still struggle with how we handle multi-scale physics problems. Things that happen like intermittent dynamics, transients. These are all things that really complicate and challenge these methods and your ability to arrive at these goals. So we'll get to some of those in the data we have here. Okay, so here's where we're going to start with. We're going to start with dynamical systems. We're going to think about some generic nonlinear dynamical system. It could be a high-dimensional state space X, and I prescribe some n, and I can evolve this. And I might have some measurements. Now, the standard way you might think about this is you write down a model here. You run that model, and you might have some measurements to compare to, and you can maybe modify your model to sort of build towards this structure. But in many cases, what we know is n ahead of time, right? So if you have a standard engineering physics background, we have all kinds of books that specify different n's. So if I take a book on quantum mechanics, it has a very specific n related to the Schrodinger equation. If I take a book up on Maxwell's equations, then I'm looking at solving E and M. Or if I take a book on fluids, I would get a Navier-Stokes representation here. These are n's that are known. They're either derived by physical considerations. Oftentimes we do these pillbox derivations, you know, conservation of mass and momentum and things of this nature. And so we can derive these ahead of time, do simulations, and understand our system this way. Now we're going to change this around. We're going to start here and say I've got a lot of sensors. Sensors, in many ways, are very cheap these days. So I'm going to take a bunch of sensors, take recordings, and what I want to do with those is if I'm measuring some complex system, I would like to discover what n is, especially if I don't know it. I mean, if you know it already, then you don't really need to do that, but the idea is if I take measurements of a new system, can I give you what n is? So that's going to be the goal. This is joint work with Steve Brunton, the Department of Mechanical Engineering here at the University of Washington, and Josh Proctor, who is at the Institute of Disease Modeling. And this is based on a paper from PNAS in 2016. So we are thinking about discovering dynamics and observables for a measured system. So how do we rediscover dynamics just from time series data alone? So the idea is the following. What could that n be? Well, a lot of possibilities. So it's really limited by your imagination. We're going to build a library of potential functions that could exist on the right-hand side. Okay? And again, really is limited by your imagination. You could think about things that are constants or linear terms or quadratics. These are like the polynomials, but also things like sine, cosine. Make up a set of library. This is going to be our library of potential right-hand side functions. This may have thousands of possibilities. Okay? And so, for instance, even this xp2, which is all the second-degree polynomials, it would look something like this. So it's all the terms like, this is a state vector from x1 to xn, so it could be x1 squared, x1, x2, all the way up to xn squared. And each row of this matrix is time t1, t2, t3, t4, all my measurements in time. So you give me a library, you give me their evaluation in time, and I have this library built. Now this is going to be my matrix A. We've talked about, I've already mentioned, this is all going to come down to AX equal to B. That's the matrix A. I can build it. You give me my state variables, take recordings in time, the matrix A is built. Okay? Now AX equal to B, the B, remember what we're trying to find is x dot is equal to some right-hand side. Well, the right-hand side can be made up of this. The left-hand side is x dot. So if you give me measurements of x1 through x of n, I could take their time differentiation. I could differentiate those to get their time derivatives, and that's b. So I'll have a, I'll have b, and all I got to do is find x. So what is x? Well, x is going to be the weighting of the library terms. And I'm going to show how this works on a simple example of the Lorentz equation. So we call this method the sparse identification of nonlinear dynamics, or SINDY. And the idea here is what we want to do is think about, for a moment, a toy example, which is the Lorentz system. And what I'm going to give you is I'm going to simulate this and produce a time series of x, y, z. So that's your data. Now, I'm going to blindfold you and say, I'm going to say, can you rediscover that even though I gave you no information about that? Well, so now you have this time series x, y, z, which means you could compute x dot, y dot, z dot. You could also come up with a whole library of functions. So you'd have A, and the B is the x dot, y dot, z dot, and the x that you're actually trying to solve for is the weighting of these columns, or in other words, of the libraries. Now the big assumption here is that there's only a few terms on the right-hand side that matter. So only a few of these columns should matter. So we're going to solve AX equal to B, and we're going to promote sparsity. I want most of the terms to be 0. The way we promote sparsity here in this specific algorithm is least square thresholding. It's a recursive least square thresholding. So you do a least square fit, you cut off all the small terms, do it again and again and again, and what you end up with is your solution is here. Those dots represent all the only non-zero components that are left over. And And when you look at those non-zero components that are left over, it gives you back exactly the terms that are associated with the Lorentz equation. Right? So you give me the time series data, a library of possibilities, I do the sparse regression, and out pops the Lorentz equation back for you. Now, of course, seems simple, but we're going to build up from there. But mathematically, that is the infrastructure, and you can see it's fairly a simple concept. What happens under noise? This is always a question that's asked. Well, if you can handle some noise. In fact, this here shows you the discovery of the Lorentz attractor with noise added to the measurements. The way we add the measurements here is just directly to the sensors themselves. We say that if I take a recording, it's that recording plus some IID with some variance variable attached to that. Okay? So we have those recordings, we can still do the regression, you still recover the Lorentz equations. Your coefficients are off a little bit more by now they're 1% off versus before they were 0.01% off. And so it still works fairly well. And as you might expect, if you raise the noise sufficiently, the whole thing breaks, right? Which is, of course, the thing that always happens. If you have enough noise in your system, and it's always going to crush you somehow, right? So it's no different here. But you can you're at least can handle some of it. Now, a more interesting example, and sort of takes it to a higher level, is flow around a cylinder. And so the idea is we're going to look at flow behind a cylinder, and what you can do is take snapshots of that flow. And now this is a very high-dimensional system, right? Because now it's XY coordinates. There's potentially a million of grid points that measure that flow around the cylinder. But if you take snapshots of that, you can do the SVD. And if you look at the SVD and you look at the singular values, it'll tell you that it's dominated by 3 modes. And that's the U matrix. The first 3 columns of U tell you what those modes are. Here they are. And the first 3 columns of V tell you how they're evolving in time. So now what you can do is you can do a regression on the time series of the 3 columns that dominate this. So in other words, the 3 columns of V. And when you do that, you actually derive the dynamics of the 3 modes is given by this time evolution here. And in fact, what you know from historical work is that this is in fact the normal form for the Hopf bifurcation that occurs for the flow behind a cylinder. And this is something that was proposed all the way in '71 by Ruhl and Takens, and finally really nailed down in 2003 by Bernd Nowak. And he showed that, in fact, if you do some very careful asymptotics and take into account the fast flow dynamics that happen in this system, you write down this equation here. So what it does for you, even though the Navier-Stokes is quadratic, it actually produces an effective cubic term by having this slow-fast interaction. And we get this directly from the data, and this was something that was sort of a very interesting 32-year history from it being proposed to it being completely solved. So this is a more serious problem, and the SINDY method really nails it down. Another interesting example or modification of SINDY is to think about dynamics that are of this form, where you have potentially some function up top versus a function below. So it could be a plus bx, and on the bottom c plus dx squared. So that's a very low rank sparse representation of both the numerator and the denominator. But when you write it in this form and you do an expansion, we have an infinite Taylor series expansion. So what you'd really like to do is discover both the numerator and the denominator. Well, one thing you could do is move this FD over here, then move this to the other side. But what ends up happening there is if you look at the solutions for that, you're going to find that, in fact, if I turn all the weightings for this and this to 0, I immediately satisfy the regression problem. So I get this trivial solution that I don't want. Instead, you can bring this over and, in fact, construct the best vectors that best span the null space of that problem. Okay? So this is based upon some optimization algorithms by John Wright at Columbia and his co-workers. And so what you can do in this case is you can generalize the SINDY architecture, to actually handling solutions of this form. And here's sort of the pathways before. Now you put a library for both f of n, a library for f of d, here they are. Now you do your regression on the null space, find the non-zero components, build your model. And this is especially important for models such as Michaelis-Menten, some of these biology, chemistry type models where you do have these fractional relationships. And what you find in this thing is that actually it recovers it very, very nicely for you. So if you take the time series data, you get the recovery of the well-known models that actually produce this, that have these fractional forms. And this is this work here, IEEE Transactions in Molecular Biological and Multiscale Physics. And it came out last year. So it's a nice modification of SINDY to handle a broader class of functional representations. More recently, with Neil Mangan, that was that previous work, and we've also built this onto to think about bringing in the ideas of model selection and information criteria to help us cross-validate the results that come out of this. So this is a recent work that's up on the archive, and the idea is the following. What we can do with this library structure is actually posit a combinatorial large set of models, candidate models. Now, in model selection, you typically are giving a small handful. The reason you do that is because if you're going to do BIC or AIC, you have to run every single model. And this is very expensive. Not only do you have to run them, but you have to run them under lots of different trials and noise configurations to get your statistics and then match it with the data statistics. So it's very expensive to do, and that's why people focus on a handful of models. But in this architecture, what SINDY, or implicit SINDY, allows you to do is consider an combinatorial large set of models. And then what it does, it says, let's look at the models that live near the Pareto front. So we can down select from this very combinatorial large set of models down to a set of models near the Pareto front. And then for each model on the Pareto front, we can down select and rank order them. So what we do now is start rank ordering them by ideas of if the data supports the model either weakly or strongly or not at all. And so these are standard ideas out of model selection. And so you can rank all the models near the Pareto front, and in fact you find in that case the Pareto front separates out nicely to give you the one model that's the correct model. And so this is a nice cross-validation methodology where all these models before were very tightly clustered on the Pareto front, and then when you do the information criteria on them, they separate out with one model being left over. Okay? So that's a nice, it's really important in terms of having cross-validation techniques for such methods. Another important innovation around this is to think about spatial temporal systems. So we want to discover PDEs. So we're going to come back to this flow around the cylinder. And this is work done with Sam Rudy, who is a graduate student here, and he has this paper out in Science Advances. It came out in spring of 2017. And the idea is the following. I want to not project into low rank space like we did before. I just want to sample the flow behind a cylinder. And what I'm going to do now is construct a library, but the library now not only has the state, but it has derivatives of the state. It could have the state plus one derivative, or a state two derivatives, or the derivative squared. You can build, again, a really interesting set of library modes here. And it's the same architecture as before. You get a large library, lots of time series data, and you're going to do a sparse regression. And when you solve that regression problem, in this case here, sampling flow behind a cylinder, you derive the Navier-Stokes equations without any kind of physical insight. You just have time series data, and you get back out Navier-Stokes. The other interesting thing about this, because there is in fact very low rank structure in the dominant dynamics, you can massively subsample the data. So you don't have to sample this massive huge dimensional space. You can massively subsample it, build the model in that space, and project back out. And you have also, you discover the Navier-Stokes that way just as easily. So it's this nice architecture, and this one here is very closely related to the concept of randomized algorithms, sparse sampling. Okay? So let me show you some nice things about this that we should also think about. One is that this architecture not only lets you reconstruct PDEs, but then it also makes you think about how I might put my sensors. So if I have a spatial temporal system, I can either fix my sensor in space, or for instance, if you're putting a measurement out in the ocean, you let the sensor itself evolve with the dynamics. So we maybe call these Lagrangian measurements, right? So our sensors are actually moving with the dynamics themselves. So the example here, the canonical example just to illustrate this, is think about a random walker, and the random walker is going to take steps left or right with equal probability and move in time as it goes across. So this is like the drunkard's walk, and you're going to measure this lots of time, and your sensor is attached to the walker. What you're going to do with this is measure lots of trials of this, and you can then construct a histogram for the different time points. And then you can do a regression to the histogram. And when you do the regression to the histogram, what you find is, in fact, that this process is governed by a diffusion equation. And of course, we've known this for a long time, that the random walk produces a diffusion process. But this recovers this in a very nice way. It also suggests that you can use this Lagrangian measurement framework. In other words, you can let sensors move with the dynamics, and that gives you a lot of information about the actual underlying structure, and in fact, allows you to recover it. There's still an issue too, however, around this idea of disambiguation. If I were to take this system here and look at these two waves, what if I only had measurements of one of the waves? In other words, I took the one off on the right. So one wave moving left to right, there are a lot of equations that could produce that. The one-way wave equation, the two-way wave equation. I could look at solutions of the KdV potentially, or NLS, that could all produce one wave moving in one direction. So how would it disambiguate between these different models? Because if I took one measurement here, in fact, what I'm actually simulating is the KdV equation, and if I just did a regression to it, it would say that it's actually the one-way wave equation, ut equals cux. The reason it would say that is because it's looking for the most parsimonious, sparsest solution, so throw away as many terms as possible and get it down to the two terms. However, if I put in two initial conditions, a high one or a low one, or I measure two sets of data under different initial conditions, it will allow me to disambiguate between all these models that produce traveling waves and actually give me the correct model, which is the KdV equation. So this is really important. What it tells you a little bit is that when you're measuring a system, you want to measure it under different conditions or different initial data so that it can disambiguate and figure out what the nonlinearity is correctly. Here's a table that I think is quite important, which is we've considered a bunch of canonical models out of mathematical physics: KdV, Burger's, Schrodinger, Nonlinear Schrodinger, Kuramoto-Shifshinsky, a reaction diffusion model, and Navier-Stokes. And in all these cases, we can find the correct model, and we can handle a certain amount of noise in doing so. And of course, if you have beyond a certain amount of noise, you have a lot of problems discovering the model, as would be expected. But it still does a very good job on these standard models. The other thing I want to mention is that a lot of these models we have out of math physics and that we write down, if you look at the form of the models, they're polynomials. So one of the both great things about this model selection is that you can put in libraries, and putting polynomials is very trivial to put in there. And of course you could criticize that and say, yeah, but what you've built in the right pieces to begin with. And you might argue, but I might argue and say, well, look, most of the models we think about and that we've derived and we work with routinely actually are polynomials. There they are. And so that we have at least a great hope that we can do quite a bit with the SINDY, the PDE find, or the implicit in SINDY architectures. Now, where can you go with things like this? Well, our hope is to go to things like this. This is a C. elegans. And it's a great model organism. It's got 302 neurons. The connectivity map is known and stereotyped. And so, and also in terms of behavioral outputs, it goes forward, it goes backwards, it makes an omega turn, or does a head sweep. So it has a very limited repertoire of actual observed functional behaviors when it's moving. And so we can start now taking these tools and starting to discover, in fact, you might have a nice model for the 302 neurons, but this seems to behave in some macro scale way where the modes produce low-rank structures across the neural landscape. And so we can start discovering potential variables that are dictating the dynamics of something like this model organism. Okay? So that's kind of a future direction that we're hoping to go in and to really get after this. Now to switch gears a little bit, we're going to come back to measurements and thinking about variables. So up to this point, we're thinking about my measurement. I'm actually measuring the state space. However, perhaps that's not the right variable to be working with. Just because you measured it or just because you wrote it down, it could be that in fact there's a better set of observables or better subspace to be working in than the ones you measured. Okay? Maybe one way to say it is, if I have a system in X that's strongly nonlinear, maybe there's a mapping to another set of variables where the system goes from strongly nonlinear to weakly nonlinear. Okay? Now just to tell you how important these transformations are, I want to, in one slide, give you a background on reduced order modeling, which is you might have some PDE, so some high dimensional state space evolving in time. You have some linear operator, which typically involves derivatives, spatial derivatives, and some nonlinearity. And what people often do is take snapshots of their simulations, they look at the SVD of that and find there's some low-rank subspace, phi of r, and then you can say, well, why would I work with this n-dimensional space when I know there's rank r there? So I'm going to go ahead and project into this subspace and now write down r equations for a of t. And here is this transformation from u to a. And now this is a rank r system. And presumably r is much, much smaller than n. So this is very efficient to solve. So that's kind of the idea of reduced order modeling, is write your dynamics in a different basis. Solve there. Why? Because it's much faster computationally because it's low dimensional. So these ideas are important, and really one of the things that we want to build on around this is the idea from Bernard Koopman and the idea of Koopman theory. And Koopman in 1931 wrote a paper around this which said, look, the basic thing is that if you give me some nonlinear, finite dimensional nonlinear dynamical system, I can define some observables of x, so it's called g of x, where now the dynamics is linear in this new set of observables. And this is an infinite dimensional space. So he takes a finite dimensional nonlinear system, projects it into some infinite dimensional linear system. Now the great thing about being in a linear system is you can write down the exact solutions to this thing. You just look at the spectral content of your operator k, which is the Koopman operator, and it tells you everything about what could happen in that space. Now, the real challenge is defining what are the observables I should be using. And that's still an open question in Koopman theory, is how do I find a good set of observables that take me from this nonlinear space to a linear space? And really the more important goal is to go from a strongly nonlinear space potentially to a weakly nonlinear space. Now, not only do we have to figure out how to define G, but we have to have an algorithm that could actually produce this Koopman structure. And that was actually realized in 2010 by Peter Schmidt, where he developed what's called the dynamic mode decomposition. Rowley and Message and others realized that, in fact, the dynamic mode decomposition was actually an execution of the Koopman operator for g of x equal to x. And the way the dynamic mode decomposition works, and let me give you a simple snapshot. This is called the exact DMD algorithm. This is by Jonathan Tu and others. What it is you take some data matrix X, which takes snapshots of your system at x1 through x of m, and then you advance all those snapshots delta t into the future. Let's call it x prime. So I want the map A that takes all these snapshots and advances them 1 delta t into the future. Well, this is fairly simple to do. You're going to multiply a times x to get to x prime. And the best way to do this is just do a simple least square fitting by finding that a of x is equal to x prime, the pseudo-inverse of x. And the pseudo-inverse, if you remember, is a least square fit. So this object here is in fact a least square procedure where it's going to produce for you the best linear dynamical system that goes through these data snapshots. There's another version of this algorithm that I'd like to highlight the work of Travis Askham, he is a postdoc here at the University of Washington. He basically developed what we're calling optimized DMD. It's an archive paper that's out right now, and this gives you an optimal way to actually create the DMD approximation, which is much more robust to noise than just the standard algorithm, the exact DMD here. Now, what are the advantages of the DMD is that it's basically an equation-free approach where essentially you're taking snapshots of the system and you're going to build the best fit linear dynamical model possible. Now, the real advantage of having that model is it has exact solutions. And that's the solutions to this give you a way to do future state predictions. And what you're hoping happens is that this model here is pretty close to the actual dynamics. That is the hope that you have. So you take snapshots of your system, you build you do a regression to the best fit linear model, which then allows you to do future state prediction and build a local dynamics that's linear. Now, where can you use this? Turns out it's been used widely now across different fields. You can do financial trading strategies with this because now you can take snapshots of the market data and look to see which way it's going, make some trading decisions off of that. I point you to this paper here with a student of mine, Jordan Mann. And this was when I spent the year at Harvard in 2012-13. We worked on this here. You can also do things like video processing and something equivalent to robust PCA, which is if I take a video frame with moving objects in a background, when I look at the decomposition, the e to the 0t term, e to the 0t is just a constant. It's not changing in time. So when you do the dynamic mode decomposition, you can look at the modes which have 0 or near 0 eigenvalues, and those are the stationary states or the background of a video. So now you can use this to take video frames, subtract the foreground objects from the background objects. And the background is just this e to the 0t terms, and then you put all the foreground objects together, and what you have is the moving cars, pedestrians, and other things like this. So a nice way to do some video processing. You can also look at sleep spindle data, and this is work with Jeff Ogemon's group here at the University of Washington, and this is work I did with Bing Brunton, who really did the core of this work here, looking at the sleep spindle data and looking at different clusters for sleep spindles, all in this diagnostics, looking at sort of patterns of activity along the brain and how you get different sleep spindle networks that arise spontaneously in this system. So it's a great diagnostic tool that hasn't been available for analyzing these ECOG recordings. More broadly, we can think about what's the difference between Koopman and DMD, because what I've said is that DMD is just Koopman. It's enacting Koopman for g of x equal to x, and so really the difference is just it's all about observables. So you take some original data matrices, x and x prime, so x and all those snapshots advanced delta t in time. The DMD just says take those, do this least square fitting regression to get yourself the best linear fit model. However, another pathway exists this way, which is instead of working with x and x prime, you work with some functions of x and x prime. Let's call those g of x prime. And we're going to call those y and y prime. Now you do DMD on these new observables to produce your Koopman operator. This is an approximation to the Koopman operator. So if you've got good observables, or if you know how to define good observables G, then the idea is you've effectively linearized some nonlinear manifold, and you've taken this nonlinear manifold, you've straightened it out to get a linear dynamics there. Okay, so that's the main idea. And what it really requires you to do is pick good observables. So let me give you an example of a model that I'm very familiar with and have good insight into maybe how I should pick observables. This is a nonlinear Schrodinger equation. Here it is here. And this is here a simulation of the nonlinear Schrodinger equation of what's called a 2-soliton, which is an initial condition of the form 2 sec c. And it looks like a little breather. Okay? And what I can do is say, well, I can construct the DMD approximation to it, which is here. So g of x is equal to x. So I take snapshots. I build a linear model to best represent this. And it actually looks pretty good. But I also know that, look, it's got this nonlinear term here. So why don't I make that part of my observables? Make g of x equals x over mod x squared x. So I take this here, and in fact, this looks really nice too. It looks similar. I'm going to show you that this is 4 orders of magnitude more accurate than this one here. Okay, in fact, it's almost dead on with the actual nonlinear evolution. Now if I make a bad choice of variables, x mod x squared, then notice my approximation is awful to this system. I've projected into a very bad direction. Now, my own personal belief is that you would always like to pick good variables for yourself. There are methods called extended DMD, which basically do something very similar to what support vector machine does, which is projects into a bunch of observables and then regresses on those observables to get you a good prediction. The problem with that, in my view, there's no problem with it. There's a lot of cross-validation required so you can get rid of bad variables. So I always advocate, if you have good insight to your problem, pick good variables and you can get something like this. Now just to show you how well it works is, we know that the spectrum is supposed to be, for the NLS and the 2 solitons, supposed to be exactly on the imaginary axis. And for this good observable, it actually is. Here's the DMD, here's this bad observable, and here's the errors of the 3. This one all the way down here, remember that my numerical scheme is like 10 to the minus 5, 6 accuracy. So I'm almost down to numerical precision of my ODE stepper. In fact, it's 4th order Runge-Kutz stepper that actually solved that, produced my data. The DMD is up here, pretty good approximation, and this other one is actually pretty poor. 2 orders magnitude off. So it does tell you that variable selection matters a lot. It's an explicit example of, like, if I can get, if you can figure out a good set of variables and I can work now on those variables, I can do a lot of things, and it starts to look very linear, and it takes a lot of pressure off of trying to really handle that nonlinearity, because you're now weakly nonlinear in some sense. I think there's a lot more work to be done there, but I think that's an exciting area of how to think about nonlinear manifolds for dynamics. The other thing I want to highlight is a couple other interesting points related to the talk, and this is around sensors and sensor networks. And really this goes with this idea of sparse sampling. There's no way in these very complicated systems that you can have full state information. You have limited information, and where you record this information becomes very important. And also this idea of multi-resolution analysis, which is in wavelets, it's a wavelet idea, which is phenomena happen on different time or spatial scales. And when you do this data discovery process, you should start looking to understand that I need to discover multi-scale physics or multi-scale phenomena as I go along. So let's start first with this idea of sparse sampling. And really this kind of came out, I got very interested in this work because of some talks I saw around compressive sensing back in the early 2010s. And started learning about this, was fascinated from the point of view of saying, actually this makes a lot of sense for a lot of physical systems where I know there's low rank structure, and so I want to take a small number of measurements to do that reconstruction. Compressive sensing, this is a cartoon from Richard Baruniak, has this idea built into it, which is if I have a signal that's compressible on some basis, then I can take some random projections or random measurements of the system, and what I can do is do solve AX equal to B subject to an L1 penalty, and I can find the sparse modes representing the solution. Okay, so that's the main idea. So you solve AX equal to B where your coefficients of the weightings of your modes that you're going to be working with is very sparse because only a few of them matter. So it's the same idea that we used before, which is to promote sparsity, but now I want to reconstruct an entire state space by taking a small number of measurements. Okay, so this is the main idea. And where we've used it is for things like, or where it comes up physically, are things like this example here. This is some measurements by Tom Daniel, Brad Dickerson here at the University of Washington. The dots you see here, this is a moth wing, a hawk moth wing, and those dots are where you have what are called the campaniform sensors, which are basically strain sensors on the wing. And what happens here is, as the wing bends, pocket of chemical comes in to activate the neuron. So it gives it information and encodes strain on the wing. So the thing we started looking at, and this is with Krithika Manohar, who's a PhD student here at the University of Washington, was to try to understand how these sensors on wings can inform flight dynamics. So as this thing is flapping and straining, can it actually understand that, oh, I've got a big gust or a small gust, I need to stabilize my flight, and I want a small number of neurons to tell me this information. So we were able to do an analysis using this kind of structure where we coupled an aerodynamic model with an elastic deformation representing the wing and understanding where to place sensors on these wings that would optimally encode flight information. Okay? So this is a very nice concept piece which starts to answer why you might have a sparse number of sensors on the wing which would be capable of informing something about the flight dynamics. So that's the sparse sensor angle, which is how do I think about a principled way of discovering how to place sensors so that I can best measure my system. Another interesting thing is this multi-resolution dynamic mode decomposition, which is the idea is how do I start now taking my data where I have fast, slow, medium scale structures happening and that I can disambiguate fast from slow and so forth. So we can start thinking about this just like you would in a wavelet dynamics, which is I can sample on a big window of time and take out the slow mode that exists there. So here is the structure. In the first pass, I would take my data, and here's my time frequency window that's traditionally you see in a wavelet decomposition, which is, at least in this big window of time, I want to take this information out and I want to go ahead and find slow scale structures. In other words, slow scale means the eigenvalues are near the origin. And I'll pull those out and those will be my slow modes. And now I'm going to go to the next level after I've removed the slow scales and look to see what's now happening on this time scale. In other words, now I went from this time scale and said what's slow here. I asked what's slow here, what's slow here, what's slow here. And at each level, I look at eigenvalues coming into some neighborhood of the origin, and those are my modes that matter. And then now I have this fast scale, slow scale decomposition architecture where I've locally built models at each level, which is a very nice idea to sort of think about disambiguating these dynamics so that I can understand what they're doing at the different scales. As a really nice example of this, I think it's a very nice example of this, is to take sea surface temperature data, which is available from NASA. You can just download this. Or actually, I think it's from NOAA. And you could say, like, well, if I took this data over a 20-year period, and if you just started looking at correlated structures, so like the SVD, what you would find is you'd find these dominant modes. So for instance, here's your dominant mode. It's just the mean distribution of temperature across the globe over the 20-year period. Okay? And then this thing actually goes up and down. That's the next dominant mode, which is the summer-winter cycle. But as you start, and in fact, you lose a lot of key features, like El Nino, because it's so small from an energetic point of view, comparatively, that you would never see it. However, when you do this decomposition where you say, here's what's happening in a 20-year period, 10-year, 5-year, 2-year, and breaking it down this way, what you find, for instance, at the fourth level of decomposition is right here, 1997, you find this mode, which is very strong in that window. And that's your El Nino mode. So what it will do for you by doing this recursive breakdown from slow to fast scales, you start to pick up key features that now do not get lost because you're sampling over 20 years. You're now cutting it down to say, oh look, in this window of time, I have this very dominant mode, and it turns out to be the El Nino mode. Now when you do this kind of shaping, I want to show you a really nice movie made by Krithika Manohar, which is, here we go. What I'm going to show you in this movie is, here is my breakdown from slow to fast. It's colored from blue to red. So blue is slow modes, red is fast modes. This is going to be timed this way. And what I'm going to show you here is a bunch of sensors. So the blue sensors, the dark blue are slow, the bright red are fast, and everything is in between those. I'm going to show you measurement locations around the globe that are capable, if I have measurements there, of reconstructing the entire dynamics around the globe. Okay, so here's a fast sensor picking up fast dynamics, a little slower, slower, and even slower. And so what we're going to see here is that at any one time, you notice that I have the yearly cycle going on, and notice the sensor placements that happen there. So they're changing locations, but the most important thing is at any one time, I only need 4 or 5 sensors across the entire world to measure, to reconstruct the entire ocean dynamics. I think this is a remarkable little video, partly because it's so fascinating to me that you have that, and more than that, not only do you need so few, but also, very importantly, notice how many of them are near land, which is a very encouraging sign, which means you could put, of course, putting a sensor in the middle of the ocean is very expensive, but putting it on land is much, much cheaper. So it tells you about how you could potentially build a sensor network that would allow you to reconstruct the entire ocean dynamics with a small number of sensors across the whole globe. And all of it relies on the fact that there's low-dimensional dynamics happening across this structure. And you've also taken it apart to highlight fast and slow features of this thing. So I think I just want to show you here is right at 1997, notice all of a sudden you have to have sensors right here to pick up the El Nino phenomena, and here it is right about there. Now you need these sensors here to pick up El Nino. And then it's gone now, and there it is again. And so now these are the kind of things you need. And so you can imagine putting just one sensor over here that would be capable of picking up that entire, predicting and picking up the El Nino and reproducing this map. So this has been a long lecture or talk. But let me just conclude by saying, there's a lot of ideas that are just integrated here. Many that are historical around model, model selection, and sparse regression's been around for a while. But we're bringing these things together to give ourselves a principled approach to deterministic dynamics. And really, what we're starting to see is that we can use these ideas to classify our dynamics, look at maybe potentially some dynamical regime I'm in, reconstruct, and also future state predict. Sorry, but I got cut off. The other important pieces is that I've covered a lot of ground, but I think it's all important because we start thinking about this structure, which is data is coming in, and this data pipe is growing bigger and bigger all the time. We're having more sensors everywhere, and so there's a problem with the ingestion of data. We can get to a point where there's so much data that just even bringing it into computer for analysis is very difficult. And that's why I talked about these sparse sensors, randomized algorithms, because we need a way to take this data ingestion in. It's not that when we take more data that the system is becoming higher dimensional. Oftentimes the phenomena we're looking at have remained the same dimension. It's just that we have more accurate sensors, a lot more data. So what we really want to do is say, there's some low-rank structure. I want to get to that. So I want to use randomized methods, sparse sampling, compressive sensing. These kind of ideas are really important on the front end of your data pipe to just bring your data down to a little bit more manageable size where you can start applying algorithms. And the algorithms you might want to apply are things like what I've talked about here, model discovery. You can build the best linear fit models through DMD, or even define some observable embedding to build Koopman operators, or you can use these regression frameworks like SINDY, PDE-find, Implicity-SINDY to actually build nonlinear models from your sparse regression frameworks. And eventually what we want to do is get to have very good prediction and very good control. And you can do this through building reduced order models, or even dynamic mode decomposition with control frameworks or Koopman control. These are all very important aspects of the entire picture. And around all this, you might imagine wrapping a learning module, which is, I've seen some low-dimensional structures over and over happening in this system. I should put this in the library so I can recall it at a later date. I don't need to build this over and over again. It's much like what we would do from experience. We would start building in key features of data that we could use later on and that we've done some work to get, and so we can use that for future state. So I think that's all I want to talk about. Hopefully you've enjoyed this. You may even made it to the end. although it's exhausting because it was more than an hour. Thank you for listening. If you want to download any of the code that goes with this, you go to my website. There's a link there that says open source code. Click there. Almost everything I've talked about, you can download MATLAB or Python or R codes to execute any of it. And so we really believe in the ability to do reproducible work, and we have all those codes available for you to get started with right away. Thank you very much.